Hello, everyone, and thank you for joining this webinar presentation. I'm Roger Levinson, CEO and co-founder of Blumind AI. I'd like to thank Sally Ward-Foxton, Nitin Dahad, and the entire team at eTimes AI Everywhere for giving me the opportunity to share with you the work that Blumind is doing in the area of analog compute, with our initial target use cases focused on edge AI applications. So let me start with a question. Is analog compute scary to you? At Blumind, we contend that staying the course with the existing traditional compute approaches is much scarier. It's clear that AI is transforming the world around us, whether it's in wearable devices, smart home, and city, or smart mobility applications. We can all recognize that devices are getting ever more intelligent. This is due in part to machine learning that is being deployed to solve these diverse problems. In the future, we see massive new opportunities in human interfaces, augmented reality, robotics, and human augmentation to enable us to perform tasks that are beyond our capabilities. As we move forward into these new areas, we will require the underlying semiconductors to deliver far greater energy efficiency. These new applications risk never coming to fruition, as we see a chip technology gap that current compute approaches simply cannot bridge. If we level up a little, we can see that the proliferation of AI in our lives also has serious negative impacts. Data centers already have a carbon footprint greater than the global aviation industry, and its growth in the future is going to be far greater. Some project that data centers will consume over 90% of all the energy generated by humanity today within the next 30 years. Additionally, manufacturing and disposal of batteries emit about 175 kilograms of CO2 for each kilowatt hour. This means that the batteries of each Tesla vehicle generate about 17 tons of carbon emissions. AI's sustainability problem simply cannot be ignored, and we at Blumind feel passionately about being one of the solutions to improve it. Here's a view on how the industry is trying to address the challenges and, quite frankly, is failing to keep up. We've enjoyed the benefits of Moore's Law for many decades, but as some of you may be aware, doubling processor capability every 2 years is not realistic anymore, and we're already at the point of diminishing returns. On the architecture front, the industry has responded by implementing incremental improvements to traditional von Neumann architecture by reducing the power loss incurred through data movement. As we move from the traditional CPUs to GPU accelerators, the energy penalty remains extremely high. To address the memory movement energy burden, near-memory architectures have been developed that have shown incremental improvement. A lot of attention has been placed on digital in-memory compute, coming in many varieties, as a holy grail for energy efficiency by eliminating much of the memory movements. However, even these innovations will not be enough, as they have resulted in fairly meager performance improvements, achieving up to 40 or 50 tops per watt. At Blumind, we've taken an approach and path to achieve in excess of 1,000 tops per watt. We've built a solution from the ground up to attack this problem head-on and break through the energy efficiency wall by leveraging the inherent efficiency of analog processing. Utilizing analog compute, we're creating a gap that today's compute approaches can't bridge and enabling product solutions that are only imagined today. We are now at a point where intelligence can theoretically be added to nearly every device, appliance, or system that we use and interact with in all aspects of our lives, from personal devices to transportation, industrial, military, and on and on. But to date, there have been some significant barriers to realizing AI everywhere. The fundamental limitation being efficiency, which is manifested most directly in excessive power consumption and prohibitive cost. Analog compute provides us the means of dramatically improving power efficiency by orders of magnitude, while providing a cost basis that is commensurate with the targeted applications and use cases. Whether or not you believe that Moore's Law is ending, analog solutions have never relied directly on Moore's Law to provide optimal solutions. The reliance on ever-shrinking device dimensions and ever-increasing performance associated with next-generation process nodes is not a requirement for successful analog compute solutions. Analog takes advantage of fundamental device physics to yield incredibly sophisticated and powerful solutions, and it is now time to apply those principles to AI computation. Analog compute holds the promise that the core computational energy of each multiply and accumulate function can be dramatically reduced by performing these functions in the analog domain. The most efficient method is to merge both weight storage and multiplication accumulation, the MAC function, into a single transistor. The industry has termed this approach generally as analog compute in memory. In this implementation, an array of memory cells is constructed, and the fundamental transistor characteristics are used to perform the multiplication and addition functions, typically leveraging Ohm's law, V equals I times R. The memory structures can be of many different varieties, such as flash memory, resistive RAM, magnetic RAM, and SRAM. Much research effort has gone into this approach, and many are working diligently to implement neural network processing solutions with this memory architecture. However, the benefits of analog compute are not being fully realized due to some significant limitations with analog compute and memory structures. Analog compute brings many key benefits over traditional digital compute approaches. Benefits such as analog is fast and easily parallelizable, leading to orders of magnitude increases in performance. With continuous data, not sampled in time or quantized, analog is able to extract the maximum amount of information from the native signals. Because analog does not require data conversion, does not require a high-speed clock, and leverages the full signal information in the power supply domain, analog is inherently much more power efficient. Noise can be a concern when considering analog processing, but neural networks are generally quite tolerant of some random noise, and in some cases perform even better in the presence of some random noise. However, to date, there have been some serious limitations with the types of analog compute that have been proposed, predominantly being classified as analog compute in memory. The challenge is that compute in memory still looks at neural network processing as a computational problem and remains trapped in a paradigm of software-driven solutions. In addition to being trapped in this paradigm, compute in memory has some real limitations. Standard compute in memory solutions are sensitive to process, voltage, and temperature variations, as well as drift over time. In addition, these architectures require costly data converters, leading to limitations of quantization and mismatch. These architectures typically rely on non-standard or specialized silicon process technologies, adding cost and limiting solution portability. Scaling can be a significant challenge combined with the difficulty of moving from one process technology node to another. Due to the uniquenesses in the structure of the solution and signal computation range, training and programming can be difficult and non-standard. The solution may have constraints of network types which can be implemented, and for various network functions may be reliant on costly digital processing elements. So how do we get the full benefits from analog computation without the limitations of compute in memory? Blumind has built a solution from the ground up in order to do just that. Blumind's analog machine learning low-power solution, AMPLE, is based upon the next generation of compute in memory, compute in transistor. This architecture provides solutions ideal for processing neural network computations while remaining in the analog domain. An example neural network graph is shown, in this case as a fully connected 4-layer network, in which each circle represents a neuron and each arrowhead represents a synapse, while each line represents an activation connection. In Blumind's AMPLE architecture, each synapse of the neural network is associated with a single transistor, which stores the weight for that synapse and performs the product of the weight and activation. The summation of the products of all the synapses is performed in the analog domain, and the neuron generates the resulting activation, still in the analog domain. In some networks, such as convolutional neural networks, some activations must be held for a short period of time prior to providing them to the next layer to process. In that case, Blumind's proprietary ephemeral memory is leveraged for that specific purpose. This architecture eliminates the need to convert back and forth between the analog and digital domains, thus eliminating wasted energy consumption and the introduction of non-idealities and noise. In addition, the architecture has the unique capability and significant advantage of being able to process analog inputs as well as digital data if needed. By leveraging precision, deep subthreshold analog design, the solution is capable of achieving nanowatt to low microwatt power consumption for standard edge use cases, such as always-on keyword and phrase detection, always-on visual wake word applications, as well as more involved vision and time series data applications. It's a common perception that analog solutions face significant challenges with noise and precision. So let's double-click on this a bit. How many of you enjoy streaming audio? Well, since this is pre-recorded, I can't really ask for a show of hands. And how many of you are familiar with how high-fidelity audio is converted from its original analog form to high-fidelity digital and then back to analog again? The answer is with extremely low noise, high-precision data converters called delta sigma modulators. These data converters are primarily analog and are embedded in standard CMOS technologies. Hundreds of millions of these circuits are shipped every year with no issues at all. In fact, you could argue that delta sigma modulators, a primarily analog function, were one of the key enablers of mass adoption of digital audio. Now let's take a look at imaging applications. All those photos and videos that we use for our AI engines to discern dogs and cats and what have you, how did those images become digital in the first place? The bottom line is that we have been converting analog to digital for decades and decades and have taken it for granted. That conversion process sets the floor on noise and precision for all the data that is subsequently processed in the digital domain with neural networks and AI. So, noise and precision are very manageable if approached correctly. That's what precision analog designers have been doing for years. For Blumind, built upon those same analog design principles, the use of purely ratiometric computation eliminates to a large extent all the first-order noise and precision culprits. Additionally, eliminating the reliance on any absolute voltages, currents, or resistances makes the architecture non-dependent on typical performance limiters. By eliminating the data converters, we eliminate quantization in the activations, maintaining maximum dynamic range. Where references are needed, we make them common to eliminate any impact on the ratiometric computations. The weights in the network are quantized to 7 bits plus sign to enable storing an entire weight in a single transistor or synapse, and these weight accuracies are maintained over temperature and time. In addition, we achieve all of this while leveraging the stability, reliability, and low cost of standard CMOS processes. Another challenge with compute in memory is its ability to scale. Being reliant on specialized process technologies has inherently limited the ability for compute in memory solutions to scale. Scalability and portability have always been a challenge for analog circuits, and fundamentally that will be true until analog design is fully automated. To overcome this fundamental challenge, the Blumind Ample architecture relies only upon the devices available in standard CMOS technologies from 28 nanometer and down. Blumind has built a solution that does not rely on any special devices or technology flows. The first manifestation of Blumind's architecture is in 22 nanometer with applications targeting voice and time series data. This is a tiny ML problem utilizing on the order of 100,000 synapses. Scaling up from there, we're tackling vision solutions for a variety of applications, both in 22 nanometer and 12 nanometer, with network sizes ranging from 1 to 10 million parameters. Our roadmap currently scales to 50 million parameters or more in 12 nanometer. This is just the beginning, as we see no showstoppers of scaling to 100 million parameters and beyond. One of the most fundamental differences in Blumind's architecture is that we have moved away from the concept of traditional compute being the execution of a program and have returned to a view that neural networks in nature are fundamentally signal processors. Signal processing does not require code to be written and compiled into a runtime executable, but rather lets the information flow through the neural network as it is processed and provide an intelligent result at the output. Therefore, we have simplified much of the challenge of integrating our solution into a system by elimination of runtime code. We do leverage the standard neural network development and training environments such as PyTorch and TensorFlow. Once we complete the standard training flow, typically in the cloud, The parameters are put in a file and uploaded in our neural network upon device power-up. We have developed an updated quantization and noise-aware training flow in PyTorch and TensorFlow to enable maximum performance utilizing our architecture. Our customers have two ways to engage with our technology. One method is to use one of our standard product SoCs, and the other is to build a custom solution for their application. To utilize our SoC, since the network is already hardened into silicon, we perform training for the specific use case using an appropriate dataset, map the coefficients to the implemented network, and finally create the weight file for upload at PowerUp. For the custom flow, we work directly with our customers to architect the neural network based upon the specific application needs, follow the same training flow, implement the solution in silicon, and follow the same weight file process. Blumind's architecture is capable of supporting a variety of neural network types. We believe the vast majority of edge devices will fall in several distinct categories of use cases, such as time series data processing and vision. The architecture can be used to implement neural networks for these use cases as well as many others. Once the neural network structure is in silicon, the network can be updated with new weights as needed to address application changes over time. The network parameters in the synapses can be updated in the field, providing tremendous flexibility. Because the architecture is extremely silicon efficient, the networks we have implemented are over-provisioned, providing quite a bit of resource for training to achieve new performance requirements over time. Due to the fact that there is no runtime code, there is no coding overhead associated with the solution, making it much easier and quicker to integrate into new or existing systems. Let's take a look at a specific example. Here is a real-world example of the power and cost benefits of an all-analog solution. Consider the case of always-on keyword detection in a battery-powered device. With the digital approach, the first cost and power impact is simply getting the audio signal into the digital domain. This takes hundreds of microwatts and can be costly. The next challenge is efficiently executing the feature extraction and digital neural network, which often entails stepping through a sequence of powering up and down functions such as audio detection, speed onset detection, wake word detection, and finally employing the keyword detection. These systems often require some storage of the history of the input audio, up to 2 seconds, which adds more power. As with all digital systems, a high-speed clock is required to run the system, thus setting a floor to the power consumption of the solution. The last piece is the power management solution necessary to manage all of the sequencing of blocks to turn them on and off in order to manage the overall power draw. Not only does the digital solution inherently cost more and consumes more power, it comes with a system management complexity as well. With Blumind's all-analog solution, we use a cheaper and much lower power analog microphone, perform all of the feature extraction and neural network processing continuously in a power budget 10 to 100 times lower than the digital system. In this particular case, the neural network and feature extraction account for a small fraction of the 8 microwatts necessary to perform the total system function, with the 2-second audio storage buffer dominating the power consumption. In the end, at a system level, power is at least 20 times lower and the cost is substantially lower as well. For applications where battery life is a primary performance specification, a factor of 20 in power savings will have a significant impact on the end product's value and success in the market. For a wearable device powered from a CR2032 battery, the digital approach could last up to a few months, while the Blumind ample solution could last for multiple years. Energy efficiency and sustainability is the #1 challenge we face with the future of computing and the proliferation of AI. Blumind is on a mission to bring ultra-efficient neural network processing to the edge and enable a vast market of devices where intelligence can be added at low cost with minimal power impact. The way forward is analog, and Blumind's ample architecture is paving the way. Analog's not scary. Analog is essential. Thank you for your time and attention. For more information, please visit our website at blumind.ai or contact us directly at info@blumind.ai.